Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on Java native interface and talk about a very important topic on how to solve the refactoring problem that we've had with JNI once and for all. And to recap, the problem is that the conventional JNI binding is tied to the package name and class name. If you recall, when we started talking about how JNI works, we said that it basically, when we run Java Edge or Java C-Edge, the C++ functions that it generates that are supposed to bind to native methods start with a Java underscore and then the package name and then class name and then method name. And the problem here is that refactoring a Java class, for example, renaming the class file, or moving the class from one package to another, breaks this description, right? This symbolic binding. And that causes a severe problem, which means, let's say it has 100, 200 Java classes. A lot of them have native methods. And then at some point we decide to refactor some classes. It causes a huge problem for how to go to C++ and correct all these bindings. Now, obviously, if we refactor the name of the Java method, then we definitely need to do some changes in C++ because this is the main point, right? So here, when I say refactoring and solving the refactoring problem, I mean just changing the package name and the class name, right? So I'm assuming that the method name is the same, the parameter signature is the same, but we want to rename the class file or move it from one package to another. Now, a lot of time when the project gets bigger and bigger, we do refactoring by just moving classes from one package to another so that we have a better organization of the Java project, right? Remember, Java is all about very large projects and maintainable code. So if refactoring breaks the JNI calls, then that poses a huge problem. And now we're going to look at the ways that we can actually fix this to some good extent. Obviously, there is no perfect solution, but there are ways to ensure that moving a Java class from one package to another doesn't break any Java to C++ binding. So how do we do that? Now, this conventional JNI binding that comes from into the header files that the Java Edge creates, this is necessary so that JVM can search for specific native methods in the dynamic library. So when the JVM loads the dynamic library, and then when we call a native method, it tries to find the symbol inside that dynamic library that corresponds to a binding to that native method. So it looks for the symbol that starts with Java underscore and then the package name of that class and then the name of that class and then the method name, right? That's the conventional binding. And then we said that if because of this, moving a class to another package obviously breaks this JNI C++ binding, because now the description, the symbol that is supposed to bind to that native method changes. Clearly, this causes a big problem if we need to refactor Java code, moving a class from one package to another. It may also change the signature of the method parameters. For example, if we move a class from a package to another package, but this class, this object of this class is basically, let's say this is a parameter for a native method, then that also changes the signature if that native method is overloaded. When we overload native methods with another native method, we need to specify the parameter signature in the function name in C++, and that may also cause problems. So using register natives, we can solve the Java refactoring problem. Obviously, it's not a perfect solution, but at least it helps us to basically get rid of the problem with moving the class files from one package to another and then not worrying about changing any C++ code. So how do we do that? We saw so far about register natives and how it works. We can eagerly bind the Java method, the native methods, to C++ functions or methods. So we create a Java class called native library loader, right? So far we've basically what we've been doing is we create a Java class that has native methods, and then inside that class we load the dynamic library. We have a static initializer that calls the system.load library. But usually we don't do that. Instead, we create a class that takes care of loading the dynamic library for us. So, and we usually put this native library loader or native loader inside a util package, a utility package. And that's the approach that I'm going to take. So native library loader is our entry point inside the C++, inside the JNI calls, right? And the assumption here is that we're not going to touch, we create this inside the util package, and then we're not going to refactor this or move it around, right? So, and then we add a private native register natives, but instead of having no parameters, we actually send a Java string which describes the class path of a particular object that we want to register native for that class, right? And then we put these register natives inside that static initializer inside this native library loader, and this takes care of loading the dynamic library for any class, right? And I also make sure that the dynamic library is only loaded once, not twice. So create a regular C++ functions that take JNI environment pointer and JClass JObject. So when we go the register natives route, we basically do eager binding, right? And then eagerly link native methods manually. So let's head to Eclipse, see how we can actually implement this. So here in Eclipse, I'm going to create a new package in my Java project, Java package. Let's call it test32. And here I'm just going to create a new class. Let's call this employee. All right. And in the employee, I'm going to have a string name and then a int age, right? And then I'm going to have a constructor, pub employee, a string name and then int age, and then this dot name is name, and then this dot age is age. All right. And then we can, for example, override it. So we can have a public native void print info, just have a native method print info, and then we're going to say that sysout so system.out.println okay. No, actually this is a native method, so we cannot have a body. So this is a native method. This is going to be implemented in C++. All right. So so this has a native method print info, and let's say later on we want to implement this in C++. But now, if you recall, if we run the Java H tool, we end up with a signature as Java underscore package name, test32 underscore class name, employee underscore method name, print info, and there is no override for this or there is no overload for this method, so there is no need for any parameter signature. We end up with this. Now obviously if we move this employee to another package, then it breaks this binding, this description, and that causes problem, right? So what I'm going to do, I'm going to create a package called util, and inside this I'm going to another thing is that we typically just load the dynamic library right inside the class, load library and native underscore C. That's because the very first time that we want to use this class is going to be loaded inside the memory, and it's going to run the static initializer. So it ensures that the dynamic library is always loaded before we use this class, which is always what we want, right? But there is a better approach. So I'm going to create another class called native library loader. All right. And here the very first thing that we need a Boolean flag. So Boolean is loaded false, and then we set it to false, right? And then what we're going to do, we're going to have public static void load library, okay? And then what we need to do, we need to actually here check for the platform if we are really creating a multi-platform Java thing that we should always do. So check platform and have private methods, private static void load Mac, for example, and then private static void load Windows. All right, and load Linux, right? For now I'm just going to focus on Mac. So, and we have already seen how to check for the platform. We just get os.name and then check the name of the OS. All right, but here I'm just going to call load Mac because I am on the Mac platform. And in the load Mac, what I'm going to say is that if not is loaded, or basically if is loaded, if the dynamic library has been loaded, and this should be static. All right, and we can make it private. If is loaded, if the dynamic library is loaded, we just return, we don't do anything. Otherwise we're going to call the system.load library here, right, native underscore C, and then set the is loaded flag to true. So this native utils, this native library loader makes sure that even if we have multiple classes and then we load the same dynamic library for each class, it ensures that the dynamic library is only loaded once. So if I have another class, let's say let's create another class, let's call it boss, and this boss has extends employee, right? It extends the employee and then name and age. But then let's say this boss has another native method, so public native void say name, for example, right? And this is native, so it doesn't have any body. Or maybe let's say hi, doesn't really matter. So it doesn't take any parameters. And then so boss extends employee, right? Now in this case, when this happens, obviously if we load the dynamic library inside the employee, it automatically, we don't need to have a static library inside the subclass, because when we create the subclass, the superclass is loaded. When the superclass is loaded, it loads the dynamic library and everything works fine. But let's assume that this is not inheriting from boss, right? So we go back here, let's just copy and paste this, name and age, and here we just say this dot name is name and this dot age is age. Now if we create a employee, the dynamic library is loaded, but and then the loading the dynamic library only once is enough, so we don't need but then if someone uses this code and doesn't create an employee, it just straight up create a boss, then the dynamic library is not loaded and we have a problem. So we need to have also system load library here, right? So native underscore C, but this causes the problem of if we create an employee, this is called, the dynamic library is loaded. If we create a boss again, and then the dynamic library is also loaded, and this is not a useful thing. We're just loading the dynamic library multiple times. So instead, we let the native library loader, this class, take care of loading the library for us, right? And it automatically makes sure that the dynamic library only loaded once, right? It sets this flag, and we know that we only have one dynamic library for our project, so it has no problem. So this ensures that this call to the system load library only happens once, right? However, there is another thing. Let's say now I want to solve the refactoring problem for this print info, which means I want to ensure that if I refactor or move this employee to another package, then it's not going to cause any problem. So after loading this dynamic library, I'm going to register natives for employee class, right? Now, how do we do that? So the idea here is that we have to signal some information to the C++. that the name of the signature of the class, the package name has changed, or the name of the class has changed, right? And remember, refactoring happens at the compile time. Refactoring happens at the compile time, not runtime, right? And this and then the binding, the C++ binding to native method happens at runtime when we load the dynamic library. So we have to signal something to the C++ that something has changed about the description of this class at compile time. So what I'm going to do is create a private static void register natives for employee, right? So I'm going to say that this native method, private static native void register natives for employee, all right? And I mean, I can make it public, doesn't really matter for now. And we have seen the register natives, and this is a native, it doesn't have any body, right? But then the idea here is that we don't, instead of having no arguments, we pass something here, and the path is basically class path. What do I mean by class path? So if I refactor a Java class, its signature is going to change, and that is reflected in the class path. Remember, in JNI or in C++, we need to have a J class, and the J class comes from asking the JVM to basically find the class and the class path. So we give it a class path for the class, right? So if the class path changes at compile time, we can actually pass it as an argument to C++ to this method, and at runtime it knows that, oh, the class path has changed, and then it can use find class and find the class again after the refactoring has happened. So let's see, how do we, and we also have seen that when we use a class, let's say employee dot class, in Java, the class path separator, the separator is dot, right? In C++, basically, actually inside the JVM, the class path separator is a slash, a forward slash, not a dot. So dot only applies inside the Java code. I don't know why they decided to do this, but this is something that you need to be aware of, right? And that's what we've been doing so far, right? So for example, employee in Java, its class path is test32 dot employee. Inside the JVM or in C++, it's test32 forward slash employee, right? So this is the difference. So let's add a main method here. So let's see. What I'm going to do, I'm going to say basically a string Java class path is employee dot class, and then let's do a sysout on this Java class path. So let's run this. So class test32.employee. So this class is basically, we don't want that. So employee.class get name. So test32.employee, right? So if I refactor this get name changes, because at runtime, the JVM has all the information about the class inside this class object in the meta space, and the get name gives us the correct description, right? So what I'm going to do here, and if I want to send this a string to Java to C++ to let the C++ know that, oh, the class path description of this class, this employee class, has changed, which means now basically change this argument to this find class. And in order to do that, I have to convert this dot separator to basically the forward slash separator. So a string CPP class path, right, is a Java class path dot replace all, and any dot that you have, replace it with forward slash. Now obviously this is not going to work, because, so first let's just print this. So let's print also the CPP, and if I run this, as you can see, all the characters were replaced by forward slash. That's because this dot is actually a regex or regular expression, and we have to escape it. And we also then have to escape the backslash itself. So let's see. Now it works fine, right? So what I'm going to do here, basically I can just add a method here, public static string get cpp class path. All right, and then I can basically do this. So return employee class get name, and then replace all right, with forward slash. And then in the native library loader here, I'm going to register native for my all classes separately. So I'm going to also have a public static native void register natives for boss. So for each class, but instead of having no arguments, which previously we saw that we put the register natives inside the class itself, and it didn't have any arguments. Now I put these register natives for each class inside the native library loader, but I'll also send the class path description of the particular class, because if a refactoring happens in Java and the class path description of this class changes, it's going to get reflected in the C++ code. All right. So register natives for employee class and also register natives for boss class. So basically we manually do this and register natives for employee. Well, I'm going to call it with the employee.get cpp class path. All right. And the same thing for boss. So register natives for boss. And I'm going to basically add the same method here, same static method here, and then here we just replace it with boss. All right, I didn't actually need to do this. I could just do it right in place. So let's copy and paste this, and then put it here, right? Remember, if I and the reason this is a good idea, because not only changing the package affects this class path, but also renaming the class, because refactoring can be either moving the class to another package or renaming the class, changing the name of the class. In both cases, it's going to be refactored in this class metadata of this class, right? Because in Eclipse, if I rename it, it also renames all the instances, all the places that I use this class. So it's going to be no problem. All right, but let's bring back the this get cpp class path, and then go to the native library loader. So get cpp class path. All right, so this is going to work for both moving to another package. Okay, let's save this, and also renaming the class itself. In both cases, this string that describes the actual class path of this employee or boss is going to be, the change is going to be reflected, and when we send it to C++, we can correctly identify it. All right. So what I'm going to do, again, we're going to eagerly load this, and when we eagerly link native methods, we don't create header files for these classes. But now our native library loader has some native methods, so we have to create a basically a header file for this native library loader. So I go to C++ perspective, select the native library loader, and then basically run the Java Edge tool. All right, and it's going to create a new header file here, test32 util native library loader, and then we have a class for the register natives for the employee class, register natives for the boss class. All right, and then I'm going to create a new cpp file, source file. Let's call this native library loader.cpp. all right, and the very first thing that we do, as always, we include that header file. So header, and then test32 util native library loader, and then we copy and paste the prototypes, these two prototypes. All right. And then we have the JVM here, JNI environment pointer, which is JVM. J class is the calling class. It's the native library loader for both of them because these are a static method, right? These are static methods. And then J string is the class path. The first one has the string representation of the class path of the employee with the correct, the dots are replaced by a slash, so it's correct. So what are we going to do? Step one, get the C++ string of class path. So const char pointer CPP class path is JVM get a string UTF-chars, and then is copy, we don't care, right? This is a step one. And then a step two, get the class, get the J class of employee. All right. So what are we going to do? We're going to say J class remember this method is dedicated to this employee underscore class is JVM find class, and this is what I've been talking about. Now, because we are sending some information from Java to C++, this class path, and this information changes at compile time if we do a refactoring on the employee, if we change its name or move it to another package. This information, this CPP class path, this changes, right? Because when the information of the employee changes at runtime, this class object that has the meta information of the class reflects all the information about the changes, the refactoring changes that has happened. And then when we call this register natives at runtime, it gets that information that the class path has changed, the name of the class has changed, or it's been moved to another package, and it gets reflected here because this statement gets executed at runtime. This is the most important point, right? At runtime, we're asking the JVM to find it on the class path, and now this CPP class path reflects the refactoring, and JVM has no problem finding it, right? So this was step two, and step three. And note that we're talking about refactoring in terms of changing the name of the class or moving it to another package. We're not talking about changing the name of the method itself. So we're assuming that the name of the method is not changed, this print info. And then that's why now we can do eager binding to C++ function. All right, so we create a JNI native method. Let's call this print info method, and then I directly initialize it with a string. So the name is print info, and the signature doesn't take any parameter and returns void, right? Doesn't take any parameter and returns void. And it's going to bind to something, so I'm going to create a namespace here, or I can use an anonymous namespace. Let's just write namespace, and then let's create a print info implement, and then we have to pass in JNI inv pointer JVM and basically a J object. Basically employee obj. The reason I'm passing a J object is because and then we have to specify the signature, it returns void, because this print info is not a static method, it's a regular method, right? So when JVM calls this method, it tries to pass a JVM object and a employee obj, it passes a J object, not a J class, right? And let's just print something simple. So I'm not going to use any field inside the employee, but this is just for demonstration. So let's include the IO stream, and then here let's just say std cout hello from print info impl in C++ and std end line. All right, and then we're going to bind this we're going to bind it to a convert to void pointer, and then print info impl. All right, and again I don't need to use this ampersand. And then let's also convert these const chars to char pointers, char arrays, right? And once we do that, now we create this method, and now we ask JVM to bind it. Ask JVM, so this is step 4. Ask JVM to bind it. So JVM register native. And the employee class, the method is ampersand print info method, and number of method we're registering is 1. All right, so now everything works fine for this employee class. Let's build this. It builds fine. Let's copy and paste the dynamic library. All right, now let's go and try to test things. So the first thing that I'm going to do, I'm going to create a test refactoring class, and let's have a main method here. And here I'm going to have test1, and in test1 public static void test1, and here I'm going to create an employee empl1 or employee1 new employee Bob with the age of 21, and then I'm going to say employee print info. So let's see if this works. Okay, so let's see what's wrong. Unsatisfied link error, native library loaded, register native for L Java lang string semicolon. Native, oh, okay, so basically the idea here is that actually we need so the problem here is that in the employee native library loader load library public static void load library load mac, so system load library native underscore c is loaded, and then so what is wrong here? Register natives, so unsatisfied link error, register natives test32.util native library loader register native for boss. So we have the header file here, and then we have the C++ here, and we are loading the dynamic library system.load library. And let's do a sysout here. Basically library, let's say library loaded. Okay, and then I go to test refactoring, I create an employee. This should load the dynamic library. So library loaded, but we still get an unsatisfied link error for these let's see, system.load library, and then register natives for employee. So the question is, why is it that this doesn't find this, it cannot run this? I guess that's because we might need to run this inside a static initializer. So load library, and then in the employee we are calling this native library loader load library, and load mac, register natives for employee, and then ut register natives for employee. This seems to work fine. test refactoring, employee native library loader, register native for boss. Okay, that's because, okay, so let's comment this out because we didn't add implementation for this boss, right? So because it doesn't have any implementation, it's being treated as a function prototype, so it cannot call it, right? Because it doesn't have any body. So for now, let's comment it out, but the employee should work fine. So let's see. Yes, hello from print info impl in C++. So we loaded the dynamic library for our platform, and then we eagerly bind the native method of the employee to C++ implementation. And so again, when we should always go with this native library loader approach. So we create a util package and create a class that takes care of loading the dynamic library and making sure that it loads only once. But it also eagerly register natives for all the classes that we have in the project that require native methods, right? So we don't create any header file for any classes. And the reason this is a good idea is that now if I refactor this person class, this employee class, notice what happens. So I'm going to create a new package, test32 package 1. And notice what happens if I move this employee inside this package. It does get refactored. The name of the class is still the same. Eclipse automatically changes the package name of the employee everywhere inside my project. But notice remember that now the class file has changed. This class path description has changed. So if we had created a header file for this employee class, for this native method, it's now changed, right? It's gone from java underscore test32 underscore employee to java underscore test32 underscore package 1, right? It has all the package hierarchy, and that breaks the binding. But with this native library loader, the refactoring is reflected inside this argument, right? Get cpp class path. And because of that, the C++ knows that remember, we need that class path to find the class on the class path at runtime, and then we register this native for this particular class. So if the refactoring effect is now reflected inside this argument, which means the JVM has no problem to, again, at runtime register natives for this correct class, right? So basically the bottom line is that this code is should still work fine, right? Even though I refactor this employee from one package to another. Now I can go even further and rename it. So refactor, rename, employee, new name. Finish. It changes the name, but again, in the native library loader, the name is also changed, right? Because Eclipse, when we refactor it in a class inside the project, it renames, or it correctly finds all the instances of that class and renames them. And now because this is changed, it's also changed here. So everything is this get cpp class path automatically sends the right information about the class path to C++. And again, we need that information to be able to find that class on the class path at runtime. Once we do that, JVM has no problem registering the native method correctly. Note that we didn't change the name of the method itself. We didn't change its signature. We only changed the package of the class or renamed the class. So basically this code should still work fine with the original dynamic library that I had. So I didn't need to change any C++ code. I didn't need to basically run JavaH again, okay? So this code should still work fine, which it does. Even though I renamed the class, I moved it to another package, I renamed it, it still works fine. So this is the main point. I hope you really understand this, and this is the most important point about JNI, how to work, because once the project becomes very large, we have lots of classes with lots of native methods. The best approach to have a single class called native library loader, and then checks the platform, loads the correct dynamic library, And then it also eagerly registers natives for every single class that we have, right? And we send the information about the class path of that particular class as the argument, so that at runtime we can correctly identify that class. Even though there is a refactoring happens in the Java side, we have no problem getting this J class from JVM at runtime in the C++ code. So again, I moved the employee class to another package. I renamed it. In either case, the original code still works fine. So I hope you understand this.